Welcome. So today I'm going to tell you about the splitting of prime paths and coverings of graphs. And this is joint work with myself, Tom Petrillo, and my advisor, Audrey Terrace. We're both at the University of California, San Diego, and you guys already know what conference this is. And so to start, I'll give you guys a little bit of background information. So in this talk, we'll be dealing with finite graphs which are connected and which are, when we're dealing with covers, we'll be assuming they're Galois, which means kind of what you think it would mean, that, well, I think everybody already knows, so we'll avoid that, but we're going to allow multiple edges and loops. We're not going to be considering directed graphs. Anyway, just to refresh your memory, an undirected finite graph y is said to cover an undirected finite graph x if, after an arbitrary assignment of the edges of x, there exists an assignment of the direction of the edges of y and a covering map which is bijective on the neighborhoods of the vertices and preserves directions. The spectator will probably think they've spotted an easier definition for covering, because I know that I have before, but after a lot of debate about this issue, the reason the definition is so complicated just comes down to having a good definition to work with loops and multiple edges. Otherwise, you could definitely form a much simpler definition for what a cover is. So we're going to envision that you have a base graph x and a covering graph y, and you're going to envision that a closed path in x, you're going to say it splits completely if, when you lift it to your top graph y, it remains a closed path. And so we're going to be interested in a few different numbers. We're going to be interested in this number I've called n sub e comma n. Here I'm thinking e is an element of your Galois group for the covering, where e is the identity element. And it's going to be the number of closed non-backtracking tailless paths of length n in x, which when lifted to y, return to form a closed path or split completely. What do I mean return? They are actually closed. Here, yeah, I just told you that, we're going to let pi sub n comma e denote the number of prime paths, not classes, in x which split completely. So you have the concept of closed paths, and then you have the concept of closed prime paths. Essentially, a closed path is almost a prime path, except a closed path can be a power of another closed path, whereas a prime path is not a power, it's simple. It can't be a power of another path. In this talk, we're going to try to attempt to calculate these two quantities. So here I'm going to give you the example which we're going to be thinking about in this talk. Up top we have a graph x, which is, I'm calling the dumbbell graph x, which we've then produced a cover of it, this graph y. The dotted line is supposed to represent the one spanning tree edge in x. Then you've lifted it to two spanning tree edges over here, and you've got corresponding lettering telling you how the projection map would work on this graph cover. So then you take this and you perform some calculations and you figure out what these numbers n sub e comma n are, the number of paths which lift and quote unquote split completely. And immediately what you notice is there's supposedly 4 paths of length 2 which split completely. So you look at the base graph and it's like, well, there's actually only there's only 4 closed paths in x total, and it's either this edge squared or its inverse squared, or this edge squared or its inverse squared, none of which are prime paths. Which is kind of surprising to you, because in just working in one graph, any closed path is going to give rise to you to a smaller prime path. So what do? We work to create some equations to calculate the number of closed paths which split completely. And what you do is you realize that it's essentially the number of closed paths in the top graph divided by the number of sheets you've lifted to the top graph. And we've got another equation for that involving the representations of the Galois group associated to this covering system. Sometimes this will be much easier to calculate than these numbers because of the size of the matrices involved. So this gives you a relatively simple method to calculate how many paths split completely. That's how I produced for you the table on the preceding page. But how do you calculate the number of prime paths with these type of properties? So the first thing you do is you think to yourself, oh, well, you know, any closed path, if it's not prime, it had to somehow start out kind of as a prime. So you realize quickly that the number of closed paths of length n should just be the sum over d dividing n, where you want to have the element sigma be an element of your Galois group and have it raised to the n over d turn out to be the identity element. And so you just add up all these different prime paths of this length. It should give you the total number of paths. Oh, this is a typo. This should be d. You want to add up the total number of prime paths of length d, for whom, when they go to this number, I've made a mistake. What I want to tell you is that when you lift so right now we've talked about lifting the path, and we lift it and it returns to itself. So in essence, you start on the sheet corresponding to your identity element. Instead, you want to think to yourself, I lift to this path and it ends up on some different sheet. You can index each of the sheets in your graph cover by the various elements of the Galois group associated to the graph cover. So you think to yourself, oh, this number pi sigma comma n, it's going to be the number of prime paths which, when lifted, that are of length n, they start on the sheet corresponding to the identity element and end on the sheet corresponding to the Galois group element sigma. So then you quickly develop this formula that, hey, the number of paths which split completely you should just sum over the d dividing n, find all the Galois group elements so that sigma to the n over d produces for you e, and then you just take the number of prime paths that end at sigma of length d. Slight typo. And so hence, what do you realize? Well, I just simplified this down for you a little bit. It means 1 over the Galois group, the size of the Galois group for your graph covering, y over x, times the number of closed paths in the top graph y of length n should just be this number over here. So what are we going to do? We're going to apply our Mobius inversion formula to this, hopefully somehow. Well, you'll notice that if n, the number of paths of length n, if n is relatively prime to the size of the Galois group, well then the preceding formula simplifies a lot, because then the only way sigma to the n over d could be equal to e is if sigma was equal to e. So then you'll determine that the sum of d dividing n of the primes that split completely for d is equal to this. So then we apply the Mobius inversion formula. You get a formula for the number of primes of length n which split completely based on the number of paths in the top graph. And so from this, you're hoping to produce some type of asymptotic for the number of primes which split completely. So as Audrey earlier today showed you, she had an asymptotic for the number of primes in a single graph of a given length. So now we have so we're able to use that theorem and apply it to this equation to produce for ourselves an asymptotic for the number of paths of length n, provided n is relatively prime with the order of your Galois group. What is it? It's just this number delta y, which is the greatest common divisor of all different of the lengths of all the different closed paths. Typically, it's equal to 1 divided by the order of the Galois group times the largest eigenvalue associated to your W1 matrix, which is this non-backtracking path matrix, which someone else earlier today seemed to be referring to as the B matrix. So there seem to be multiple letters to go here. with here. In general, you can use one of the previous equations on the previous slides to realize that the number of prime paths of length n, which split completely, have to be less than or equal to, essentially less than or equal, as opposed to equal to the preceding page, of 1 over the Galois group of your cover, y over x, for the number of closed paths of length n over d in your top graph. So thus, you can combine these two things and realize you have a growth control condition on the number of paths, number of prime paths of length n, which split completely for a graph covering of y over x. Namely, they can never be big. They're always bounded from above by this delta y over the size of your lift times the maximum eigenvalue associated to this W1 matrix. And so what would be better to know is how can you create a better asymptotic in this non-coprime case, and how can you do better if you're interested in paths that end on a different sheet than the identity matrix. So it's 6:05, so I'll let you go.